And we'll use the calculator for the logarithms, but the graphs, we already know what they're going to look like, so it's kind of silly to continue on with that. We started 3-2, where we have fewer objectives, which is good. It usually means it takes fewer days. So modeling real-life situations using exponential growth with decay. They actually started doing that in exponential algebra, and we've been doing it ever since. So lots of repeat. I'm not sure that we'll get to this until Monday, find an exponential or logistic model for a real-life situation using regression. In fact, we probably will. So we started yesterday by just looking at a situation that had a constant percentage rate that it was changing by. And brought back memories of y equals a times 1 plus r to the t from Algebra 2. But when we got down to this box, we saw that this book uses different letters, but it is the same concept. We have a constant growth rate or decay rate that we're looking at. So the letters may be different, but it's the same type of thinking. And this is strictly for population, whereas our y equals a times 1 plus r to the t was for any situation where you had that constant percentage growth rate. It's the same thing, just thinking in terms of people instead of, or actually any number of things if we're talking about population. If a population P is changing at a constant percentage rate R each year, then we can use this little bugger. P of T, standing for population, equals the null population. That's what that little sub-zero means, and that is initial population. What did it start at? And then the one that's part of this formula was connected to this chart. And then when you look at it and you get kind of tired of doing this over and over and over, you realize, well, this is 100% of what we had originally. And then we're just tacking on some more. Whatever the increased percentage was, in this case, it was 2%. So down here, we should not be shocked to see that 1 because that's the 100% of the original. And then we're adding whatever percentage they give us. And then T, while you can think of T as time, it's better to think of it as time periods. How many time periods is this going through? So that gives us all of the good stuff. In this formula, it says just think of T as time in years. And that's if we are looking at each year, what's happening to that population. Now, this could be used for decay. In Algebra 2, we actually had a separate formula for decay. The only change in that formula was that there was a minus in here instead of a plus. So keep in mind that this can be used for decay. We'll just think of it as a negative when we're looking at all of this and put in a negative r instead of a positive r. Everything that's in this parentheses set right here is called a growth factor or a decay factor. So we're going to know whether or not it's growth or decay just by looking at it. We'll see, hey, that's a number bigger than 1, that's growth. Hey, that's a number that's less than 1. Oh, that's decay. And what's in those parentheses is called the growth or decay factor. So we're going to jump right into it here. We've had several pages of just jumping into it and going, and that's what we're going to do today. So example 1 says, let's find growth and decay rates. Tell whether the population model is exponential growth or exponential decay. Let's just stop right there. So take a look at this. Find your base. Remember, we have initial population, then the base raised to the number of time periods. And I want you to think, is that growth or decay? What is it? It's growth. It's bigger than 1. So this is going to be growth. I'm not writing the word exponential growth down there because really they're going to be exponential. It's just which ones are growth and which ones are decay. And then find that constant percentage rate of growth or decay. So this comes from thinking backwards in that formula about, hey, it was 1 plus something. Well, that rate, that percentage rate that we need is the something. You know, what did they add to it? And it's pretty easy to just subtract the 1 off of this one and see that we have 0.0064. And then we'd have to move the decimal over 2 places because we want to talk about this in terms of a percentage. So this would be 0.64%. Now the 1.0064 would be called the growth factor. You know, that everything that would be inside those parentheses is the growth factor. But they were asking us for growth factor. This one said specifically that we were supposed to tell them the constant percentage rate of growth or decay. Done. It's growth. And there it is. I did a lot of yakking through that one because I want you to get every little piece of this. But I think Detroit can go a little faster here. Which one is our base in Detroit? Yeah, 0.9858. So is this growth or is this decay? This is decay. That's less than 1. So they had something in there they subtracted from 1. So for Detroit, we know we have decay, and we want to figure out what did they subtract. Well, we can use subtraction to do that. I mean, if we take 1 minus 0.9858, that'll tell us what it was they subtracted from that. So that's exactly what we do. 1 minus 0.9858. 0.0142, which would be what as a percentage, everybody? 1.42%. So that's what we write. Decay. And the decay was 1.42%. So San Jose, their population has been increasing. We saw that yesterday on a graph that we did. But Detroit, due to the fact that a lot of their automobile plants closed, their population is actually declining. That causes all kinds of crime problems. So they're going to have to figure out what they can do to get some jobs back in that city. Example 2, finding an exponential function. Determine the exponential function with initial value of 12, investing at a rate of 8% per year. Well, we've got the formula for that. T equals null population, 1 plus increasing t. Well, we need to know what the initial value was. Do we know that? Yeah, it's 12, they said. Initial value, boom, there it is. Did they tell us what it's increasing at? So our job is really to say, okay, 8%, I can't use that because I've got to put it into a math formula. I have to change that back into 0.08 to the t. And then, of course, we do a little simplifying. And again, I'm doing this in baby steps. You probably could have just that answer. But we want to make sure that we're remembering, hey, here's our basic formula. Now here's what we do. Again, if it's a decrease, we subtract instead of add. That's going to be the only difference. So that's the exponential function that takes care of that. Cool. That wasn't too tough. Down here, we've got exponential growth and decay models. All right, finally, hitting that objective really hard. Used for populations of animals, bacteria, even radioactive atoms, any situation where the growth is proportional to the current size of the quantity being studied. So, you know, especially that radioactive part, they use that a lot to try to figure out how long something's been decomposing. So example 3 says we're going to model some bacteria growth. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Now, here's what I wanted to remind you. In some of these, T is going to stand for years, days, hours. But notice how my label changed for all of those. So when we see something that fits our exponential model, we need to realize that X isn't always, pardon me, as straightforward as we think it is. X needs to be how many time periods we have met. So sometimes it's years. Sometimes it's really easy. You just do T equals years. You know, sometimes it's days. T equals days, and we're good. In this case, it would be X equals whatever we've got up there. But sometimes we have to put a little more thought into that. So with this one, it says they've got a culture of 100 bacteria. Cool. That's what we're starting with. So P of, I'll use T again for time, 100. I'm looking around for a number for what is the increase here or the decrease, and it says the culture doubles every hour. So what would that be multiplied by every hour? 2. And since they said that we have every hour, if we're using T up here, we want to quickly come over here to the side and say, you know what, T stands for hours. So that we know what unit we're supposed to use as we talk about this problem. So there's our model, and it says predict when the number of bacteria will be 350,000. Well, this is one I'm not going to use my graphing calculator for a graphing feature. I'm going to go back to the good old algebra here. Say, all right, well, I need that t. If I need that t, the first thing I do, divide by 100. That's going to take 2 zeros off this little monster over here. Now, I want to gain access to the t. Right now, I can't get t because the 2 is in the way. How do you get rid of that 2? Log base 2. Those are inverses. On the other side, I've got the old-fashioned calculator, so I have to use the change of base formula. And the change of base formula says you take the logarithm of the big number you're trying to evaluate, which would be the 3,500, and you divide it by the logarithm of the base. So we're going to do log of 3,500. Divided by log of 2. 11.773. What was our label? Hours. Right there. Now, since that's in hours, what we probably want to do is say, you know what, we can do a little bit better than that. We've got 11 hours here, but maybe we could tell them minutes. So if we take that 11 off, because we already know that that's hours, we could multiply that by 60, and then we could give them minutes. So 11 hours, approximately 46 minutes. And if they needed it, I mean, really, they'd have to tell us they want this very, very accurately. We could also do seconds on this. But this is probably going to be close enough for somebody to say, okay, I've got some time to go have some lunch or something while I wait for this bacteria to grow, because I've got 11 hours, 46 minutes. And I've got quite a while to do this. So for the interpret piece, what we want to do is put this into words and go back and put it in the context of the problem. So what they were asking us to do was predict when the number of bacteria will be 350,000. So one sentence can take care of all of that. The number of bacteria will be 350,000 after approximately 11 hours and 46 minutes. And while we were doing that problem, I was thinking I should have checked to see if anybody needs a calculator. Does everybody need a calculator this time? Everybody's set. We're going to be using that for our logarithms here. So this last part is important. I had talked yesterday about registering and about how if you know you're not going to go into a math field, although AP Calc is super easy, I know you guys will really enjoy it. AP Stats is also an option. And this is a big part of AP Stats right here. AP Stats is, okay, go back and talk about what this means in terms of the problem. So something to keep in mind, a little more English involved with AP Stats. And yes, this said, solve graphically, we've done enough of that, you know. It's putting our equation in for y sub 1, putting that 350,000 in for y sub 2, finding the intersection. That's a great way to check this problem, but you really should be using your logarithms that you learned in Algebra 2 for a lot of this. So on the next page, we have some more wonderful stuff here. Exponential decay functions model the amount of a radioactive substance present in a sample. I actually had a little more stuff down there. You guys, was that the bottom of your page? Okay, so we are in the right spot. Then it's like we skipped a little something, decided something wasn't necessary. Exponential decay functions model the amount of a radioactive substance present in a sample. The number of atoms of a specific element that change from a radioactive state to a non-radioactive state is a fixed fraction per unit of time. The process is called watching to see how much of that radioactivity does it contain. And the time it takes for half of the sample to change its state is called the half-life. Makes sense. Half of it has changed its state of a radioactive substance. Half-life is a concept that's used a lot in medicine as well. It's where they get their expiration dates for medication. When whatever it is that they're prescribing to you loses half of its potency, it really shouldn't be taken anymore. So that's why those expiration dates are on there. Modeling radioactive decay. Cool. Suppose the half-life of a certain radioactive substance is 20 days. Uh-oh, that's new. That's a little weird. Okay, so it's over 20 days. 5 grams present initially. All right, so that's what we're starting with. Find the time when there will be 1 gram of the substance remaining. All right, we're going to need a model. But to do that, we've got some weird stuff going on over here with the time, this 20 days business. So I start thinking, I need to know how many time periods this is going to take. And each one of these is broken up into 20 days. So out of 20 days, 10 is what portion of 20 days? Half. So this is really only half a time period when you have 10 of something. If you have 20 days, 20 is what time period of 20? Is the whole thing, it's 1. If you have 30 days, how many 20-day time periods do you have? 1.5, you know, they're 30 over 20, which would be 3 halves if you want to leave that as an improper fraction. If you have 40 days, how many 20-day time periods do you have? 2 of them. 50, how many 20-day time periods? 2.5, yeah, 5 halves. So you start to notice what we're having to do with that 20. We're having to take anything that we have for time and divide it by that 20. So that's a really important part of trying to figure out what we're going to have to use for our exponents when we finally write our exponential model. So now I want to write the model so that I could go over there and do that grams remaining stuff nice and easy. And they said there were 5 grams initially. I have 5. How much of the substance is left after those 20 days? Half. It's a half-life. So this is what it's changing by. And if you wanted to use 0.5, you can certainly do that. But most of the time we keep this a half because it's called a half-life. So it just makes sense to do that. And we can't just put T on this. We found that out. This has got that goofy 20-day period. So we had to use T over 20 whenever we were calculating how many time periods this has. So you can't just think of T in terms of time. You have to think time periods. So now, what are we supposed to do? Well, we're supposed to fill that little chart. And if we have 10 days and we put a 10 in here, 10 divided by 20 was 1/2. So all we're really doing is using this formula and putting in different fractions for our powers here. So we have 5 parentheses 1/2 to the, and in the first case we would have our 10 over 20, which would be the 1/2 power. So it would have 3.536 grams remaining. Next up would just be, okay, we know 20 divided by 20 is 1, so maybe I'll just cheat and do second enter and come in here and do a little deleting. The delete button is right next to the left of the left arrow button, so that's where delete is. And that would give me 2.5, which makes perfect sense. We maybe wouldn't even want to use the calculator for that one because half of it would be left. And then 3 halves, so second enter. 3 divided by 2 parentheses. 1.768 grams. Change it to a 2. 5 grams, which again makes perfect sense if you think, well, that'd be half of a half. So half of our 2.5 would be 1.25. And then our 5 halves. So 0.884 grams left. So for filling that table out, you know, that's all we have to do. It's basically evaluating, putting that in. Now, that doesn't answer their question. Their question was, find the time when there's going to be 1 gram of the substance remaining. Well, that means, when will this come out to be 1? And let's not solve this graphically. You've got this picture in your notes. We know how to do that already. Let's solve this one by hand. So how do we get that 1/2 to the t over 20 by itself? Fine, you don't need me. Maybe I'll just give you the answer. You're all already doing this. 1/5 equals 1/2 to the t over 20. You're gonna need some logarithms, right? What's the base of your logarithm? 1/2. And you could change it to point. You could change 1/5 to 0.2, and you could change 1/2 to 0.5 if it's easier to punch in. So we'll have the logarithm of 1/5 divided by the logarithm of 1/2, but that's going to equal t over 20. So our last step is going to have to be doing what? Multiplying both sides by 20. So we're going to need 20 times the logarithm of 1/5 divided by the logarithm of 1/2 to give us that time. We already have it. Adam, what'd you get? 46.439. Sound right, everybody? Okay, so 46.439. 46.439. What? What were we trying to find? How many days? Yeah, this was all in days. Now, this is another one where we might want to change this into days and hours. You know, instead of just leaving it 46.439 days, we might want to say 46 days. So tell me how many hours that would be by taking that 0.439 times 24. About 11. So if somebody asked us, you know, we wouldn't want to try and say 46.439 days. You know, we try to be a little more accurate and say about 46 days, 11 hours. So our interpret is that last sentence where we pulled this all together. And what we wanted to know was, and I'm scrolling up to find that, when's there going to be 1 gram of this substance? So there will be 1 gram of this substance after approximately 46 days and 11 hours. You know, just like we were talking this earlier, like they asked you, okay, how long is it going to take for this to get down to 1 gram? Just put it in the sentence. Interpret what it is you're trying to find. Well, that's a lovely problem. Again, could have been done by graphing. You know, we could mess with the window and make sure we can see it and find the intersection. But like I said, I think we've done enough of that. We need to get some more practice for logarithms. Scientists have established that atmospheric pressure at sea level is 14.7 pounds per square inch, and the pressure is reduced by half for each 3.6 miles above sea level. Okay, so that gets me thinking. That's kind of like a half-life. You know, if it's reduced by half, it's kind of like they're still talking about half-life here. For example, the pressure 3.6 miles above sea level is half of 14.7, which is 7.35 pounds per square inch. This rule for atmospheric pressure holds for altitudes up to 50 miles above sea level. Now that's new. That's new information here. So this formula is not going to work for everything. it's just going to work up to 50 miles above sea level. Though the context is different. The mathematics of atmospheric pressure closely resembles the mathematics of radioactivity, obviously. So, we need a model. All right. P of T equals, so what were we supposed to use as the start? 14.7. And what did they say this is going to increase by? Like a half. Yeah, it's just like our half-life. But again, we got something goofy going on here. And that is, we have to figure out, kind of what are those time periods going to be. In this case, it's kind of like thinking about how many cycles there would be with this. And it reduces by half for each 3.6 miles above sea level. So let's see. And this was that days business. We took our numbers and we divided them by 20 because the cycle was 20 days. So if this is the cycle, which is 3.6, that means we're going to have to divide by that to figure out how many time period cycles that we're talking about. Now what do they want? Find the altitude above sea level at which the atmospheric pressure is 4 pounds per square inch. Well, we can do that. We need to know when this is for. How do we do it? Then what? Yep, log 1/2. Got to get rid of that 1/2 to gain access to the base. We don't punch in until the end, so we're going to have the logarithm of 4 divided by 14.7 over the logarithm of 1/2. And then what are we going to have to do? Multiply by 3.6. Get it already? I'm punching in, isn't it? Yeah, they punch one of these in like this so that it see all of this. So we have to go with 6.760 for this one. And then think, well, what does that mean? 6.760 what? Well, this really wasn't time. Even though we're using T, it wasn't talking about time. It was talking about the miles. This whole thing was about miles. So the atmospheric pressure of 4 pounds per square inch will be reached at approximately 6.760 miles above sea level. So going back and putting that in the context of the problem, they said the pressure is reduced by half for 3.6 miles above sea level. So this was all going to be above that sea level point. Beautiful, looking good. Now, got a whole page of you try, but looking out here the last couple of problems, I think you've already been trying a lot of these. This one's a little different, and that's because we're back to population, so we have to think about that whole 0.5 business that goes on when the census is keeping track of people. Tell whether each of the population models is exponential growth or exponential decay. Find the growth decay rates and factors for each. and use the model to predict the current population. Well, let's start here. San Jose, growth or decay? Growth. Growth factor of 1.0136. That's the growth factor, everything that you would be raising to that power right there. But that's not the growth rate. What's the growth rate? 1.36%. All right, so we've got the growth decay rates and factors for each. Use the model to predict the current population. Oh, well, t equals 0 represents 1990, but we know better. 1990.5. And now, yeah, we're a few days into January, but we can think about this as really 2018. So we have to take 2018 and subtract that 1990.5 to figure out, all right, how many years should we be tucking into this thing? So how many years are we talking about? Don't forget the 0.5 piece. 27.5. So this is just an evaluate thing because we're trying to find t, and then we'll just plop it in the calculator. So p of t equals 782248 times 1.0136 to the 27.5 power. And go ahead and punch that in. And remember, we're talking people. We have to round to the nearest person. Everybody getting 1,134,164 people? Okay, good. Yeah, because you're already on Detroit. I can see that already. All right, so we go to Detroit. Was Detroit growth or decay? It was decay. And the decay factor is 0.9858. But that's not the rate. Did you get the decay rate already? 1.42%. Well, let's check that out. 1 minus 0.9858. Yeah, 1.42%. Did they use the exact same numbers that we did on the other day? Oh, rats. We should have changed those up. Now, this time, we're talking about 1980. So we'll have to do 2018 minus 1980.5. So what are we going to put into that one? Yeah, an additional 10 years, 37.5. All right, so let's see. That one comes out to about 703,000. 848 people. And again, whether or not you use the approximately or the equals is not a big deal because we know what this one we would have to do around it. All right, San Jose and Detroit. Hopefully we're done with those. We've used that example several times. Small culture of 10 bacteria, put it in a petri dish. If the culture doubles every hour, after how many hours will the number of bacteria reach 500,000? Tell me how you're starting. Starting with the 10. Doing what to it? Multiplying by 2. to the t. And you might want to use H for this one. Maybe the letter will help you out a little bit. H for hours. Doesn't make any difference, but whatever you use there, make sure you use the same variable when you do your function notation on the other side. So where's the 500,000 going to go? There. So basically you're taking the 0 off over here. We had 5 of them, now there'll be 4. Then what do you do? Log base 2. So those of us with the older calculators, I probably could find some more space over here. Log of 50,000 divided by log of 2 equals H. What'd you get? Well, you're still calculating. Oh, yep, I got ahead of you a little bit there. So let's wait until everybody gets that one punched in. Hide it for a little while. 15 point what? 610 hours. This would be another one where I would convert the hours into minutes. You know, just because we can. Give them a little bit better than that. So if you take that 0.610 times 60, how many minutes are we talking about? About 37. 15 hours, 37 minutes. And yeah, on a test, we wrap that up with a sentence. Say, it will take this bacteria approximately 15 hours, 37 minutes to reach 500,000. That's a lot of bacteria. 15 hours, 37 minutes. Number 3 says, what if the initial bacteria in example 2, instead of doubling every hour, tripled every hour? Then we do a new prediction. So does that change the amount we started with? No. It does change what it's going up by. So instead of 2, what do we use? 3. And we want to know now with that change, when can we expect that 500,000? So what do we do? Divide by 10, takes a 0 off. Then, just the base of our log changes here. And we punch her in with the change of base, which I don't have room to write there. Log of 50,000 over log of 3. And punch that in. Let's see how many hours we're talking about. And then we'll convert it into hours and minutes again. So we're a little more accurate. Here we got it. What you got? 9.849, right? Hours. And if we take that 0.849 piece times 60, how many minutes are we talking about? About 51 minutes, yeah, so 9 hours, 51 minutes. Again, we could round that off with a sentence. The last part says, what would the model be with T in hours if the population was tripling instead every 7 hours? Interesting. So this means we have to think about our time period a little bit more. So P of H equals, still starts with 10, and this, they're talking about the last one, so it's still a 3 here, but what are we going to have to do if that changes to every 7 hours? Divide by 7. Yeah, we'll have to do H over 7. Now again, it says we're supposed to think of T in hours. We can't change that. So for B, what are we going to have to do for our power if it's a day, but thinking in hours? Yeah, we'll have to divide by 24. Well, this one might be a little tougher because it's kind of thinking backwards here. 20 minutes in hours? How many 20-minute periods are there? So this is going to be 3H. It's just thinking back. For a while we've had to cut things up to get our time periods, but with that one, we had to multiply to go the other way. So, that's some good exponential stuff we did there, and fortunately for us, there's more! Woohoo! So, we're still working on model real-life situations using exponential growth and decay from our objective. And this one says, determine the exponential function that satisfies the following conditions and define the units you're going to use for t. So we're just going to use t for every single one, but we're going to tell people here's what t stands for. And we're just writing them. They're not having us use this for anything. So let's see. We've got, well, they want t, so we'll definitely do p of t. How do we write that there's an initial value of 7 and it's increasing at a rate of 32% per day? What do we start with? The 7, yeah, it's the initial number that we start with. Increasing at a rate of 32%, I don't think we have to do this in steps. What would we need in the parentheses for that to happen? 1.32. All right, and this one says define the units that we will use for t. So in this particular one, what would you use for t? That day, per day. So t could just stand for days. Number of days. All right, B, initial value, 427. Got that. Been there. Decreasing at a rate of 0.427%. Oh, we might have to grab a calculator for that one. Decreasing at a rate, so it's going to be 1 minus that as a decimal. Okay. So 1 minus 0.00427. Oops, no parentheses there. 0.99573. Well, I've used the whole thing. Just to make sure everything's accurate. But then we need to raise that to something. What would you use for a t in this one? A year. Yeah, it says per year. Why not? For C, P of t equals, what do you start with? 18. Quadruple point. What does that mean? Quad, how many? 4 to the t, but they said we have to define t. So it says every 13 minutes. Now there's going to be a couple of ways for us to do this, but I think if we stick with what we already know, we'll be okay. So if this is every 13 minutes, what should we do with this? Put it over 13, yeah. And say t equals time in minutes. Stick with what we already know. Just use t over 13 and have that work. Oh my goodness, here comes some weirdness. P of t, initial value 26.3, having, seriously, fortnight? 3 fortnights. Okay, put this into something we know. A fortnight is 2 weeks. So if you have 3 of them, how many weeks you talking about? 6 weeks. So what should we do for a power? T over 6, where T stands for what? Yeah, number of weeks. That's goofy. To be honest with you, when we first did this book, I thought this is the first book I've ever had that still talks about fortnights. Fortnights is something from way, way, way in the past. Renaissance age for fortnights. 5. Suppose a radioactive sample loses 43% of its mass every 9,876 years. That's a long time. What percentage of its mass will be left after 2,000 years? Let's see. So, I'm tempted to use R of t, but we'll go ahead and use P of t equals. Initial value. Okay, well then we better use a new variable. Let's just put x in there. That sounds good. All right, if it loses 43% of its mass, how much is it keeping? 1 minus 1.57. Every 9,876 years. Oh my goodness. So if we want to stick with what we've been doing, what would we do? T over 9876, where T is years. Wowie gazowie. Now, they wanted to know what percentage of its mass will be left after 2,000 years. Well, where would the 2,000 go? That would go in for T. You're thinking, how am I supposed to know about the percentage? You're thinking too far ahead. Let's figure out what we'd have so far. This would be 0.57 to the parentheses 2,000 divided by 9876. So P of t would equal initial value times 0.892. Wait a minute. That is the percentage that's left. So what is that as a percentage? Notice I didn't clear it because I want those 3 decimal places. What would that be as a percentage? 89.240. So it turns out we didn't need to know what the initial amount was. You know, it's always, no matter what we put in here for x. Now, if that bugs you, because you're thinking, oh my gosh, I would so want a number in there. If you are working with percentages, a great number to use for x, because you can use any one you want. A great number is 100. Put in 100, you get your percentage back. But I hope that that algebra is going to work okay for you there. So the next one says, after how many years will the sample contain 22% of its original mass? Okay, well, we just found out that we don't really need the x. What we need to know is, when is this? Going to be at 22% of its original mass. Well, I can't use 22 over there, because when you take something that's a percentage and you put it in an equation, what would we change it to? 0.22. Well, I think we can handle that with logarithms mighty fine. Now, we could certainly graph this. Absolutely could, but we can get logarithms here too. So what would we do logarithm-wise? Yeah, picky little base is 0.57 here. So this will be t over 9876 equals the logarithm of 0.22 divided by the logarithm of 0.57. So at the end, we'll do what to it? Multiply by 9876. And how many years later? Well, it's radioactive stuff. It's going to take a long time. So log 0.22 divided by log 0.57. Multiply that by 9876. That's a lot of years. That's a lot of years. So 26,602.068 years. why not change this into years and days? Because it's so big anyway. 26,602.068 years. Most people are going to say, as it gets closer, let me know. I'll be 6 feet under, but somebody give me a call and let me know that this is actually happening. The point here is radioactive stuff is going to take a long, long time to decay. My guess is it's too close here. Well, we almost made it to the day 2 thing because I was thinking last night, I think we can make it through the rest of this. So Monday we'll talk about Chernobyl. Woo. There's the worst one. You remember the worst one? You guys were around for the worst one, right? Japan. Oh my gosh. They're going to have glow in the dark fish that speak to them. They really are. Oh. Not good. Not good. You can probably make it through that. You can probably get through day 1. Yeah. They'll be fishing off of there and pulling the line, and the fish will say, "Put me back." Quite frankly, I can't believe they would drink any of the water on the island of Japan forever. Unfortunately, they've been through that before. Alrighty. Away we go. Happy weekend. I know everybody's been hanging on. It's just like you. It's a really tiring week. 4 days. It's a long, short week, right?
Like,
We get Martin Luther King Jr. Day off.